everyone. Thank you for attending this session. My name is Fan Yang, and this is Wei Huang. We are both from Apple. I feel really lucky, like our session is right after Pooja's session, because Pooja just shared all the complexities of managing all this kind of data platform engineering thing. And today we are going to share some of our thoughts and experience, and actually we'll do a live demo about how we propose to solve those complexities after day 2. So we are going to explore the tenant-centric strategies to simplify multi-tenant and multi-cloud complexities in real life. Here's today's agenda. So first we will briefly talk about background and the challenges and pain points we are facing in our daily life as a platform. We will share our goals by doing this effort, and we will share the high-level architecture about how we propose to solve the complexities in multi-tenant and multi-cloud. In the end, we will share more details on the implementation with a live demo to give you a simple example of how we solve these things end-to-end. So first, let's talk about the background. So as you can see on the screen on the left side, it's a very typical kind of code structure about how we manage our infrastructure code or configurations in for the infrastructure code or configs in our system. It can be multi-cloud providers, and we will have multiple accounts or regions. And of course, you can break this down into polyrepos, but that doesn't solve the complexities overall. So not mentioning if you are introducing multi-tenancy to your system, the complexity of this whole structure of the hierarchy will add up. Because we are dealing with a number of the different vendors, accounts, regions, resource types, the volume of the cloud resources will be very substantial. Also to note, these configurations are oftentimes not consistent across environments. For example, large language models. And large language models need GPUs and beefy GPUs like A100s, H100, H200s. But not all these GPUs are available in all the regions we have. So if we want to host large language models, we will need to consider the availability of the GPUs and provision the GPU machines in our Kubernetes clusters accordingly. That means we need to look through all these configurations and making sure we can put the configuration for the node pool correctly, right? Also, because of the different cloud providers, they have different APIs that will add more complexities into our system when handling similar features across different cloud providers. So really considering all these complexities from infra or platform team perspective, we need a programmatic approach to manage all these resources in a more efficient way. So this is talking about infra and platform team pain points. On the other hand, we also have end users. So end users, they are facing a different kind of types of the complexity. And here, end users can be application developers or DevOps engineers, SREs, or even infra engineers itself, because we are leveraging the platform to manage our resources based on our needs. The good thing for the cloud native community is that everything is open source and it moves really fast. However, the downside for that is today we are facing so many different tools because we have so many choices, which is a good thing. But all these tools, they may offer different kind of APIs on how to manage all these resources underneath. Plus, we may have different tools for different environments as well. Giving one example for ingress. Maybe we will choose Nginx or Traffic for our regular ingress purposes. For some machine learning clusters, we may choose AI Gateway as an ingress solution. So in that case, as an end user, they might deal with different tools or even different APIs when they want to provision ingress for their different workloads. And also, the APIs difference can happen on the tool side as well as the cloud provider side. Which means the end user, they need both very deep understanding of how each tool works, as well as sometimes they need strong debugging skills when an issue happens. So talking about the pain points from both platform engineering as well as end user perspectives, here is a simplified layers for our platform system. So as you can see on the left side, it's actually the infrastructure layers. So on the bottom, we have different cloud providers to help us provide hardwares and facilities for running our workloads. And Kubernetes actually does a very good job of abstracting all these APIs for the users, so that applications don't need to worry about the different APIs from cloud providers. All they need to do is follow Kubernetes API and define standard Kubernetes objects, and Kubernetes will help provision like compute, storage, network for them. On the right-hand side is actually the user workflow. And before we do this journey, our users are dealing with all these tools directly and to manage all these infrastructure layers, like Terraform, ArgoCD, Spinnaker. It's pretty complicated, especially when migration happens, because in that case, people need to deal with multiple tools, the old tools as well as the new tools. So similar to Kubernetes, I think oftentimes there is a missing abstraction layer to abstract the tooling for the end user, so that they just need to be consistent on their infrastructure requirements. Everything underneath for managing all these cloud resources can be abstracted away, and we can hide all this complexity behind the scenes. To summarize, our goals is basically we want to define an abstraction layer to unify the tooling and cloud provider. And we want to introduce programmatic templating for cloud resources. That means we will have code generation and configuration fan-out. The platform has to be API-driven, especially when we are dealing with like tons of different accounts and regions, so that we can make sure it's consistent and scalable. The last but not the least is we want to enforce the schema-based control and automation so that we can manage the expectations on user behaviors. Here is a high-level architecture about our proposal. Let's take a look from left side to the right side. So from the left side, the user will start with their infrastructure requirements based on this predefined schema by the platform. And once they check in their requests, like for example, they may want a bucket for storing data, or they want a certain DNS record to talk to their services. We will use Pico as a templating system and Prow as a Git flow engine to help generate the actual resource claims for users based on their requirement to the actual cloud providers or clusters. And then once the output gets generated, ArgoCD will pick it up and sync it to Crossplane control plane clusters as the CRs, and Crossplane will provision and manage resources accordingly. Because everything is managed in Kubernetes in Crossplane, we can actually easily leverage the native Kubernetes labeling system so that we can build a very thin layer of platform API server that we can allow users to specify certain selector criteria so that they can filter and get all the cloud resource object information accordingly. And this API server will fulfill the gaps of the end-to-end automation. Think about, for example, if a user just wants to deploy a certain workload into a cluster with certain Kubernetes version or even kernel version, and if we can expose those information as a label in the Crossplane CRs, they can actually talk to the platform API server to easily retrieve the cluster information. The same thing can be applied to Prow so that everything can be programmatic without kind of human interactions. Let's dig a little bit deeper into two parts of the architecture. The first part is really about the templating system and the code generation. So we choose Pico as a templating language because Pico is a has a strong type system, which is very beneficial for the schema and data validation. And then Pico also support module. We can reuse the Pico modules, and we can even version those modules as we go. Pico also has a very good support with a Golang. It also has a safe defaults and override system. Lastly, it has a very good IDE support, which allows us to have easier adoption in our system. For the Git flow engine, which is Prow, because it's GitHub native and open source friendly, we really like the plugin system for Prow because it can easily extend features as we need. By adopting Prow, we also follow chat-ops and a label-driven Git workflow. The whole idea for the templating system and code generation is basically we want to simplify the definition from user side for the infrastructure requirements, and then we can actually automatically generate everything for them behind the scene. And even for migrations, any user doesn't need to deal with the complexity of the migration. They have to just stick with their requirements. Here's a simple example of how it works, and we will demo more in our live demo. Is on the left side is one of the typical user input if they want to have a bucket or storage bucket in the US East 1 region called X. And this is a Pico format, and of course you can use a JSON format or YAML format. It's up to you how you do the code generation. And then in the end, the Prow and Pico will help them generate the actual resource claim on the right side. So on the top is a S3 bucket called X in US East 1, and at the bottom is a GCS bucket in GCP, also called X in US East 1. So in this case, user doesn't need to consider how many accounts we have, how many cloud providers they have. All they need to do is they need to just specify certain criteria about their requirements, and everything will be automatically generated for them. The second half is about how to actually manage the resources after we generate the configs. So we choose Crossplane because it's Kubernetes native, and as I mentioned earlier, because everything is managed as a Kubernetes object, we can easily build labeling system on top with the API server. Also, Crossplane itself can be very easily to extend to further abstraction objects. Like for example, you can define a cluster type or cluster CRD, which can be eventually translated to EKS or GKE clusters. Also, you can, because it's all CRDs and operators, you can even write your own operator in CRD for define anything customized. Like for example, if your team is using Spinnaker to generate pipelines, you can even write a CRD for Spinnaker pipeline, and a user can define from the platform perspective the same way as they define the standard cloud resources. Also, it has a dynamic provisioning and reconciliation, which enforces us to follow the code-driven development. Because if you manually change anything without checking the code, Crossplane will revert the change because it respects the code as a source of truth. ArgoCD itself has a really good integration with Crossplane, and is very declarative and multi-tenant friendly. And also the ecosystem of the ArgoCD community looks very promising for us too. Next, talk about implementation. This is actually a very high-level journey we have went through, and we are still ongoing. Is in the V1 version, we actually started with Crossplane ArgoCD. We even manually checking the Crossplane claims so that ArgoCD can sync it up to the actual Crossplane clusters to manage the cloud resources. Then we introduced a tenant-centric API, which is YAML-based. So users just define the YAMLs, and we will do preliminary schema check. And we also have an in-house code generation webhook to convert the tenant YAML into Crossplane claims. In the V3 version, we introduced Pico to conduct more strict schema and data validation, and we did better Golang integration with Pico data. We also introduced Prow to streamline the PR generation. As of now, in progress, we are working on leveraging Pico and Open API to provision this generic platform API server so that we can chain all the missing pieces end to end. And also, because we love Pico so much, we are also in progress of modularize more Kubernetes manifests in our system to replace some legacy JSONs we have in our in our shop. Next, I will hand over to Wei for a live demo to show you more details.
All right. Thanks, Fan. So let's do some demos. So in today's demo, I prepared 2 repos to showcase the full end-to-end flow. The first repo, also I call it upstream repo, is called kubecon Japan, which is basically define 2 things. One is the schema, that is the class of the resources you want to offer to your users. And the other is the data, that is the user input, to adhere to the format of the schema defined here. And then once that data is checked in, we will have some code generation process to generate the eventual the YAMLs that will be picked up by the Crossplane. So for now, they are set to be sit in the underscore output. So that means it's an auto-generated thing. And all the code generator code is using the Prow's external plugin mechanisms, all the source code here, and also I uploaded to my personal repo. So let's do the first PR. That is, let's say we have 2 tenants, and they want to spin up some buckets in whatever the organization has the cloud accounts. So let's first dive into the schema definition. Maybe it's pretty new for you guys because it's written in Pickle. So Pickle is a strong type language. And underneath, it's, I think, a JVM based. And then the grammar is a little like Java. So in this resource config.pickle, it basically tells you, I want to offer my end user to abstract the definition of Kubernetes resources like namespaces, as well as buckets. So today's demo will use buckets. And buckets is just some name and region. And we will have code gem components to find that out. And for the tenants to provision their buckets, definitely they need the accounts. Either they can be different cloud providers, and also we want to impose some tags to show their purpose so that we use the label selecting to dynamically do the matching. And here you can see that we can restrict the cloud provider, and then for the user, it will be hard for them to make error. For example, if we define some errors here, the IDE will show you. So basically, it follows the principle of shift the validation left instead of postpone it to very long time to do this on 5 fingers. So, and then with the account in place, and then I define some tenant specification of the desire of the resources I want. So here I define I want create a production level buckets in US East 1. So basically, in the folder here, we put some opinion here because according to our operation of the clusters of the products, basically they are pretty inclined to use the environment-based pipeline. So we just put that specific opinion here, that is the folder represent the environment name. Other than that, we don't restrict how and what they want to put into their resource request. So basically, this tells the system that is tenant X wants to create production level buckets, and it doesn't need to know what accounts in the system. And you may guess that according to the accounts definition, we have 2 accounts, right? So it will fan out. The codegen component will fan out 2 buckets, one in GCP, one in AWS. And also, we define another tenant called tenant Y. That is, instead of defining the name and region, it additionally defines some provider to show the desired accounts. Here shows the accounts. You can define some other, like you want to some specific region, etc. And also, it wants to create both dev level and the production level buckets in the AWS region. Then let's check in the PR, the code. So I'm gonna checking this, ensure that the input is correct. Because underneath we are using Prow as a CI, as the, I should say the process of how to guardrail the approval of a PR. So if you're contributing to Kubernetes, you're pretty familiar with Prow. So basically, it requires you to need some reviewer or approval to ensure the proper labels, approve, and the LGTM on this. So I'm switching to another accounts, which is my plove.io account. Never mind. And then I will LGTM. So UL means some reviewer will review the user input data, and then the Prow will kick in to label it LGTM, and then we'll merge it. And then the code merge doesn't mean anything, right? So we implemented some of the code generator components using a chat ops manner. That is, you say code gen. No matter it's pre-merge or post-merge, because if the PR is not merged, the downstream PR will not be generated. We should wait for a while, and then underneath the code gen component, which will run as a Prow plugin, will get the signal and then fetch the content based on the PR star value, and then do some parsing about the input data and do the code gen in a stateless way and generate all the exact desired resources in the downstream repo. OK, it kicks in and auto-generated. Let's take a look at whether it's generated the resources as what we want. So we define a production level bucket for tenant X, and it doesn't specify any restriction, right? So basically, it generates in the AWS as well as the GCP. So this one, yeah, and also it auto-generated the customization because we want it to be auto pick up by the ArgoCD. Also for the tenant Y, it generates two buckets. One is dev level, one is a production level. Because we specific the desire of restrict that provider to be AWS, so it didn't touch anything up in the GCP account. And again, we need someone, reviewer or approval, to approve this PR. And also I set some CI-based CI here. I'll let it run. So I will LGTM, where's that? And approve. So we need to wait for a while. During our waiting for the PR to be merged, I will show the fundamental setup a bit. So we leveraged Prow. So we have a couple of deployments here. We leverage two essential plugins in the Prow system. One is called Hook, which is basically a GitHub event hub that will forward the event to whatever external plugin that is registered in this setup, which in this case is our in-house KubeCon PR generator. And also we are using the in-tree type plugin to control the overall PR approval process. Because the upstream already developed Prow for a long time, so you can reuse the owner's system. If you're using Kubernetes a lot, you are familiar with that. So basically, you define who can approve or review which folders files, and that is organized in an inheritance way. If you define some approval in the sub-level, and that sub-level will kick in, can be act as the approval. But in this repo, I just simplified, define a root level owners file. OK, let's go back to the PR. OK, it's generated. Oh, sorry, it's merged. So yeah, that's just the end-to-end flow. But I will do a second one. Let me go back to my upstream repo. And do the second one to show you how in the daily operation, how we change the spec of the input. For example, in this case, for example, someday a business requirement says, OK, we don't want the AWS account to be served as both dev and production purpose. And we may want to say, for the AWS account, we want to give it some text. And when it's type text, you can see the IDE shows up the prompt. So it's very hard for you to make an error, typo here. That is because Pickle is already fully integrating into the IDE. That is what we also want, the validation ship left. And also, whatever the available keys also can be prompted. So in this case, we want to say this address will only be used for production. And then we check in this and see what would happen. So in this case, because we add additional restriction to this, so that in the tenant X, it won't generate the bucket in the GCP, right? Sorry, it's a tenant Y won't get the dev bucket because it says it wants to only provision the bucket dev in AWS, but AWS now is production-only accounts. So let's check the PR and create it. And the other thing we build into the system is that sometimes a reviewer, it's hard for them to detect what's the potential code gen. So you don't need to wait for the PR to merge and see what's the potential diff. You can say code gen drag run. And also the code gen component will kick in to generate a PR downstream, but immediately close it, because it is just for the reviewers to visualization on the potential diff. Let's wait for a while. Refresh a bit. Yes, it generated a PR and then immediately close it. So as a reviewer, you can see the potential changes might be generated in the downstream. So in this case, it's as what we expected. It's the deleted bucket Y, which is be restricted because the AWS account only for production purpose. So yeah, that's pretty much for today's demo. And then as a summary, this framework is generic enough for we abstract the resource requirement use our customer API. In our internal platform, we define further what's the authentication will be like, because in different provider, you may have, in AWS, you have ISA, you have EKS extensibility, access entry. In GKE, you have the workload identity. In GKE, you also have the inherited IAM, etc. But that is too much for the user to learn. So we define the simplified layer to abstract the requirements as an API. And the Pickle-based templating help manage the configuration in a very programmatic way. And personally, I love it because every time I write the Pickle code, I know I cannot make errors. So it's very hard for me to make errors in Pickle. And the code generation is the way to glue the system, the upstream, downstream. And also, we have some legacy system. The code gen can also target into those systems that is not managed by Crossplane. And all resources can be labeled and filtered using leveraging the Kubernetes principle, that is the label selector. We borrow the principle from that. So yeah, that's pretty much for today's session. Thank you. And I think we can take maybe one or two questions. Yeah.
I have a question. I'd like to ask about the implementation of Pickle. It looks has a type inference. Is that based on the static, how to say, is that just macro or some static type inference?
So in the Pickle definition, we define the class. So the class will leveraging what the Pickle defines that to ensure all the fields are typed. And then if you define the namespace, for example, the namespace in an integer, and then you will just error out. This is just leveraging what the Pickle has. And one additional thing we leverage from Pickle is the Go binding. So look at this definition for the resource config. It will correspondingly generate the Go code. See here. That's the resource config. That is auto-generated. So that enables us to use our most familiar language, for example, Golang, to consume the input Pickle, and then do whatever, in this case, do the code gen very easily. And what we use in the downstream is just called the load from pass in the downstream. In the package, yeah, that is just one line for code. Get from the Pickle data, convert it into Go objects. That's super convenient. That is what we really use Pickle here. Yeah.
Good. Thank you.
Mm-hmm. All right. I think we are running out of time, but we will be around. So you're welcome to ask us for any further questions. Thank you.
Thank you.